Let's begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. And I just pray be with us today. Help us again, Lord, to glorify you in what we do this day. In your name I pray, Lord Jesus. Amen. Okay, so where are we? Apparently America still. Yay. What? Did I say something? Let's see here. We're on lecture 27. So, we get to it. So lecture 27 is mostly on the factorization of polynomials, something you already know a little bit about, but I think we'll add to your knowledge a little bit today. Before I get to that, of course, I have something left over from the last lecture that we should do. So this is the definition, an important definition going forward here. A principal ideal domain which we abbreviate as a PID, all right, is an integral domain. What's an integral domain? Commutative ring with unity, right? Such that what? Yeah, no zero divisors. So it's an integral domain R in which every ideal is principal. What's that mean? So in other words, I, an ideal, implies that I is generated by some particular element of the ring. And you'll remember that that is just notation for RA such that R is in the ring, right? So there's the ideal generated by A. Any questions? Okay, so here's a theorem. If F is a field, then the polynomials over F, Fx, is a PID. All right, so first of all, we proved, maybe was it last class? I don't know. Recently, we proved that the polynomials over a field are what? We've shown that F polynomials with the coefficients from the field forms an integral domain, right? So what is left to do? We need to show that every ideal is principal, right? So let I be an ideal in F in the polynomials, all right? Then what can you do? Well, a couple different cases. First of all, an easy case. If the ideal is just the zero ideal, well, that's generated by zero itself. So it's principal, and we're good. Right, so the zero ideal is principal. So otherwise what? Otherwise, I is not equal to the zero ideal, right? So if you look at the set, let's call it S for a second. Look at the set S, which is called the degree. All right, the degree of G of X. I'll tell you the degree of F of X. Let's say F of X, such that F of X is in the ideal, and f of x is not equal to 0. I need f of x not equal to 0 to make this set well defined because the degree of the 0 polynomial is not defined, right? But otherwise, the degree is what? It's either 0, 1, 2, 3. Them's what? Counting numbers, right? So by the well-ordering principle, this has to have a what? By the well-ordering principle, S has a smallest element, right? Say, degree of g of x, right? So consider that g of x. I'm going to argue that that g of x, all right, that element of least degree does what? I'm going to argue that that generates this, this ideal, all right? So let me go through the argument here with you. So g of x is the polynomial of least degree in I. It's not the, it's a polynomial of least degree in I, all right? So let f of x be anything in the ideal, all right? Then we can apply the division algorithm, right? Then there exists q of x and r of x in the polynomials, right? With what? With the degree of r of x less than the degree of g of x. To be more clear, with either r of x is equal to 0, right? Or the degree of r of x is less than the degree of g of x. And in both cases, we have f of x is equal to what? F of x is equal to q of x times g of x plus r of x. This is the division algorithm, right? So then what? Well, if you look at r of x is equal to what? R of x is equal to, what's it equal to? Well, it's equal to f of x, right, minus q of x times g of x. Now, where is f of x from? F of x is from the ideal, right? And where's g of x from? Well, g of x is from the ideal. If we take anything in the ideal and multiply it by another polynomial, it's still in the ideal. So this is in I, right? And if we take the difference of things in the ideal, it's still in the ideal because it's a subring, right? So this altogether is an element of I, right? So what does that tell us? Right? What's that mean? What does that force on r of x then? Can it be non-zero? Well, no, it can't be non-zero, right? Because g of x is the element of minimal degree. So if r of x is non-zero, that's a contradiction to g of x having minimal degree. So this implies that r of x is equal to 0, right? So therefore what? F of x is equal to what? F of x is equal to q of x, g of x, right? Which is an element of what? That is a multiple of g of x. That's an element of the principal ideal generated by g of x. So what does this show? So I've taken an arbitrary element. You may have said it, I just didn't hear you. I've taken an arbitrary element in the ideal, right? And I've proved for you that it's in the principal ideal generated by g of x, right? So therefore what? I is a subset of this, right? Is the other inclusion clear as well? In fact, yes, it's easy to see. Maybe you guys can tell me why. Why is it also true that this is a subset of I? Well, I mean, this is kind of dumb. This is what? These are multiples of g of x, right? But g of x is in the ideal by assumption, right? So those things are also in the ideal. So this inclusion is also clear from the definition of principal ideal and the fact that ideals are closed under multiplication. So we have double containment. So therefore, I is equal to the principal ideal generated by g of x, which proves every ideal in the polynomial ring is principal. What are the ideals in the integers? I'll let you think about that for a second. This theorem, this proof also gives us another theorem. If F is a field, all right, and I not equal to 0 is an ideal in the polynomials over the field. The wording here is confusing me. I'm just saying g of x is a polynomial, all right? Then, I think this is Galilean's wording, I think. Then I, not my fault, I is the ideal generator. I mean, it probably makes sense. Anyways, then the ideal is generated by g of x if and only if g of x is a non-zero polynomial of least degree in I. So all this theorem is saying is that, hey, if you look at this proof we just went over, if you want to find the generator of an ideal in a polynomial ring, all right, again, it's important that the coefficients for the polynomial ring are taken from a field, but you know, a polynomial ring with field coefficients, such an ideal can be generated by the element of least degree. So that's all you got to do. You just got to find the element of least degree, which is in there, and that'll do it. So get back to my other question. Can you guys tell me what are the possible ideals of the integers? So here, my question was, what are the ideals of z? What's that? The primes. I mean, I think 2z is an ideal, as an example. But that's prime. Fine, that's prime. 3z, also an example. But you know what? So is 4. And so forth and so on. Actually, nz. The question is there anything else? The answer happens to be no. And you can give almost the same proof as I just went over here for the integers. You pick an ideal, then by the well-ordering principle, there's an element of smallest degree, and you can run through pretty much the same argument here to show that it's generated by that element of smallest degree. So I asked Professor Smith yesterday, I'm like, so I don't know, I mean, I did this construction of formal polynomials with you guys, and I'm like, but you know, something about it leaves me kind of like, you know, what's the point? And he's like, well, in his taste, it basically gives you some object which is formally equivalent to the integers. So thinking about what I just said, that starts to make sense, right? Like, if there's an argument you can give for polynomials, there's probably a corresponding argument you can give for integers, right? The division algorithm for polynomials and the division algorithm for integers, the proof of those two things, very much the same. And there's this interplay between integers and polynomials that you can see and study as we go on in here. An example here, which is nice. Let me work through it. If you look at phi, I'm mapping from the polynomials with real coefficients to the complexes. all right, defined by the evaluation, basically. So phi of f of x is going to be defined to be f of I, all right? So of course you can, I mean, I would just argue and just claim phi is ring homomorphism, all right? I won't prove that. But I would point out that the kernel of phi then is an ideal, right, of R of x once we have that, right? So it's an ideal of a, where? It's an ideal of a polynomial ring with field coefficients, right? So what's that say? It has to be generated by the polynomial of least degree in the kernel, right? Or at least a such a thing. So that implies that the kernel of phi is equal to g of x for some, the ideal generated by g of x for some g of x, right? And what would it, could it be a linear factor, right? Could it be a linear factor? Like what if you had phi of mx plus b in the kernel? What would that say? That would say that mi plus b is equal to 0 for m and b real numbers, right? But this is absurd, right? Because that says that b is equal to what? Minus mi, which is preposterous, right? Why is that impossible? We have a real number equal to an imaginary number, right? You cannot do this. This is not possible. By the structure of complex numbers, this is not possible. All right, so therefore, the generator, right? The generator of this kernel has to be at least quadratic, right? So if you observe then, hey, if I look at phi of x squared plus 1, that gives me I squared plus 1, which is 0. Therefore, x squared plus 1 is an element of the kernel of phi. That has to be a generator because it's the element of smallest degree. It's an element of smallest degree. The smallest degree is here in non-zero polynomials too, right? So therefore, the kernel of phi is equal to the ideal generated by x squared plus 1. You guys with me? I hope. Now some of the homework problems you're like facing at the moment don't have this technology intended yet, right? But you see, part of the reason I've assigned you the homework problems that I have in Galean, where you're tackling maximal and principal and all these different terms, is like you're facing them without too much to work with right now, and sometimes those questions are kind of hard. But as we go on in here, and you look back at those homework problems, they'll start to get easier if you use the theory we're developing here. I mean, there's something. Anyway, so that's more a comment for studying for the next test than it is for the current. But anyway, so by the first isomorphism theorem, what do we get? We have that the domain of phi, mod the kernel, right, is isomorphic to the image of phi, right? By the way, you can easily see that that phi is a surjection, right? Can you guys prove it? How would you get a plus bi over here? Phi of what gives you this? What's that? Very good. Yeah, so definitely phi is a surjection, right? So this translates into just R of x mod the principal ideal generated by x squared plus 1 is isomorphic to the complexes. And there you go. We have said before that this looks kind of like it, right? What I'm showing you right now here is actually a complete proof of that assertion. No, fine, I didn't. Fair enough, I didn't show that that's a ring homomorphism, but modulo that detail, you know. So, yeah, complete, just not complete. Okay, so, sorry. Moving along. So, where was I? Next, we're going to define irreducible versus reducible polynomials. All right. So definition. Let D be an integral domain. We say f of x in the polynomials over D is irreducible if whenever, let me skip a line here, if whenever f of x is equal to g of x times h of x, all right, then what? G of x or h of x is a unit in d of x. A non-zero, non-unit element of d of x that is not irreducible is known as a reducible polynomial. This is the worst sentence in this chapter. So let me put it in other words for you. A polynomial that is not reducible is reducible. Okay, so I mean, let me be a little bit more clear here anyway. A non-zero, non-unit, non-zero, non-unit element of d of x, which is, so much writing, not irreducible over d is reducible. All right. And I have committed a cardinal sin of this chapter, a sin of omission, but it's a very unfortunate sin of omission because this is actually kind of mission critical for going on here. It's irreducible over D. Okay, context matters a lot here. Yeah.
How similar is this to considering like prime ideals?
The connection between prime ideals and the connection between the connection between prime and irreducible is interesting, but we're going to get to that in a future lecture. Sometimes they're the same, and sometimes they're not. But in many familiar circumstances, they are the same. So if your intuitive spider sense is tingling, perhaps you should listen to it. I think it's maybe legitimate. All right, examples. Example 1, f of x equal to x squared plus 1. So what's the deal here? This is irreducible over the reals or over the rationals, right? But if you look at f of x is x plus I times x minus I, you can see that it is reducible where over the complexes, right? Or even just over the reals where you've adjoined the imaginary number I, right? In fact, you could also, so this is also reducible. You could also say it's reducible over Q adjoin I. So this is the set what? This is Q adjoin I is this guy. The point is that you need that imaginary number in there to split it. Right? Let's see another example. Any questions? You can break in here for questions if anytime you want. F of x, you have to speak up, I'm not going to turn around. 2x plus 4. And unlike Jenny, I don't have eyes in the back of my head. Let's see here. So, she's a mom, so it's part of her job. Let's see here. So 2 times x plus 2. So f of x equals 2x plus 4 is irreducible over the rationals. All right, but it is reducible over the integers. See, 2 is not a unit in the integers. But 2 is a unit in the rationals. Because 1/2 is the multiplicative inverse, right? So that's the difference. That's not an interesting factorization in the rationals. But it is an interesting factorization over the integers. So the question of what are the units in your set, your ring, is pretty important. Example 3, if we have f of x equal to x squared minus 7, well, you know the song and dance here. This is x plus root 7, x minus root 7. All right, so this one is, let's see here. It's irreducible over Q, but it's reducible over the reals, right? What are the units in the reals? What are the units in the set of real polynomials is what I'm really asking. That's actually the same question as what are the units in the reals. They're just non-zero real numbers. There's no way you can take a polynomial, right? Multiply it by another polynomial and get 1, unless you're dealing with a constant polynomial, right? Yep.
For the above example too, why is x plus 2 not a unit in Q?
Because there is no x plus 2 times f of x, which is equal to 1 for f of x in the rational polynomials over Q. So that means that there's no solution to this. X plus 2 is not a unit. What is a unit? A unit is something that has a multiplicative inverse. So it doesn't, so it's not. Let's see here. Example 4. Again, we can look at x squared plus 1. A lot to learn from this polynomial. Depends on its context, though. And here we're going to assume this is an element of z3 of x, okay? Now, check it out. So f of 0 is what? F of 1 is what? F of 2 is what? I'll start you out. 1, 2, right? Yeah, 5, which is also equal to 2. The point is, f of x has no 0 in Z3, right? What did we prove last class? We proved that a polynomial over a field has a 0 if and only if It has a factor corresponding to said 0. So this means that there are no linear factors in this polynomial, which means that it is irreducible. You cannot factor x squared plus 1. The only thing you can pull out from that, it would be a unit. Actually just a constant in this case, right? So I mean, this implies then that f of x equal to x squared plus 1 is irreducible over z3. Now, here's an interesting contrast. You could look at z5. Same thing, same polynomial, all right? Look at it in terms of z5. So what do you have here? I mean, I show various ways to, I mean, it's pretty obvious that if you plug in 2 to that, right, you get 0. 4 plus 1 is 5, which is 0. So you know that you can peel off a factor of x minus 2. So then you can go looking for it. Or here's the way most people do this kind of thing. You're like, wait a minute. So I'm just going to rewrite that as x squared minus 4, since 1 is equal to minus 4 in z5, right? And then it's the difference of squares. So there it is. Just like I was saying, 2 is a 0. Well, guess what? The other 0 is minus 2, aka 3. Or you could just plug in numbers. You could find that f of 2 is 0, and you can find that f of 3 is 0. That would imply the factorization is x minus 2 times x minus 3. X minus 3 is x plus 2, mod 5. So, in short, reducible, right? But again, you should complain, reducible what? Over z5. I mean, that complete the thought is important. I mean, I know in this context, you know I'm talking about z5, but you got to be aware of that. Reducibility and irreducibility are always attached to the ring of coefficients which you're considering. Theorem. Can I erase these? I think I don't need this anymore, per se. I'm going to go over here. And I feel like today I've got nothing to prove. So, theorem. Suppose F is a field. F is a field. And f of x is in the polynomials over said field, has degree 2 or 3, all right, then f of x is reducible if and only if f of x has reduced, I just did it again, reducible over f. If and only f of x has a 0 in f. I'll read through the proof. It's very understandable. If f is a field, and if you have a polynomial of degree 2 or 3, what does that mean? Well, first of all, if f of x is reducible, right, that means it has a factorization. The factorization has to have a linear factor in it, at least one, right? But last time we proved that every linear factor corresponds to 0. So if it has a linear factor, it's got a 0. That's one direction of the if and only if. And then conversely, if f of x has a 0, that means you can factor out x minus c times g of x, which means it's irreducible. Excuse me, which means it's reducible. So this is a very, very nice theorem, because it kind of extends our factor theorem a little bit further. We can't go much farther, though. This fails at order 4. All right, but first, let's enjoy the fruit of our labor here. Actually, I'm not going to enjoy the fruit of our labor. I'm going to give you a cautionary tale of order 4. What example am I on? Example 6. We will use this, rest assured, in future examples, so just keep it in mind. If you look at f of x equal to x to the 4th plus 14x squared plus 49, well, that's a quartic, right? This theorem doesn't apply to that. But if you look at this, this is x squared plus 7 quantity squared, right? Now, in other words, it's the product of two polynomials of smaller degree, neither of which are units. So this is a reduction of the polynomial. This shows that f of x is reducible. Over what base ring? I mean, over what fields of coefficients, or rings of coefficients, if you like. I mean, this is definitely true over what? Over the reals, if you like, right? You could put it's rationals, right? It's reducible over the complexes. I mean, whatever. This is a reducible quartic, and it has no zeros in any of those. Oh, wait a minute. Scratch that. No zeros. And yet it's reducible. So this theorem breaks down at 4th order. All right. All right. The next few results in Galilean here involve the interplay between the integers and integers mod p or something like that. All right. And basically this notion of the content of a polynomial is central mostly to the proofs, but I do want to talk a little bit about the proofs, so we better introduce it here. The content. What's the content of a non-zero polynomial? Let me give it some an x to the n, an minus 1 x to the n minus 1 plus plus say a1x plus a naught. This is going to be a polynomial with integer coefficients, all right? What is the content? It's the greatest common divisor of the coefficients. If the content of f of x in zx is 1, then we say f of x is primitive. All right. So, example 7, if we had something like f of x equal to 2x, 2x squared plus 4x plus 8, right? The content of this polynomial, all right, is what you can factor out. So that's 2x squared plus 2x plus 4. Right? I mean, the greatest common divisor of 2, 4, and 8 is 2. Right? So the content is that. And what's going to happen, if you factor out the content, what you're left with, right, is something with the greatest common divisor of the coefficients is just 1. So when you do this, it's going to make whatever's over here primitive. This is the idea. Now, it so happens that this is also monic. What's a monic polynomial? Right, so if I have something like x to the n plus an minus 1 x to the n minus 1 plus da 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 plus a1x plus a naught. This is monic. And that implies primitive. Of course, I'm talking about the context of polynomials with integer coefficients here. All right. So, I told you guys I have nothing to prove. So I'm going to pick up on that theme right now. The product of two primitive polynomials is, guess what? Primitive, yeah. And the proof of that is rather beautiful. It involves this interesting fact. If you have two rings which are homomorphic, all right? If you take the homomorphism of the two rings, and you can apply that same homomorphism at the level of coefficients to the polynomials over those rings. So like there's a natural homomorphism between polynomials with integer coefficients and polynomials with mod p coefficients. The homomorphism is just given by taking, you take your polynomial and you replace it with the polynomial where the coefficients are calculated mod p. That's the homomorphism that goes from the ring of polynomials with integer coefficients to the ring of polynomials with z mod n coefficients. And so this is notion. So in this section, chapter rather, Galilean, he puts a bar over things to indicate this homomorphism. I've typed up a little bit more. I'll let you read it. We can talk more about it next time you have questions. But anyway, get to the point. The product of primitive polynomials is primitive. And then that brings us to the real event, which is that if we have f of x in z of x, all right, so polynomial with integer coefficients, if f of x is reducible over q, then it is reducible over z. All right. Let me show you an example rather than the proof. I think I've cleaned up the proof though in my notes for what it's worth. So where are we? Example 8. So if we have f of x equal to 6x squared plus 19x minus 7, you can look at that as f of x equals to 6 times x squared plus 19 over 6, x minus 7 over 6, right? And okay, well that's 6 times what? That's 6 times x plus 7 over 2 times x minus 1/3. So check it out. F of x reduces over q. And of course, that's also equal to what? Multiply the 6 through. Basically, you pick the 3. The 6 is really what? It's really 3 times 2, right? Or 2 times 3, if you like. If you study the proof of this theorem, it's basically based on stripping out the content of each of the polynomials in the reduction and then like reassembling them, which is exactly like what we're doing in this example is exactly what the proof is that I'm skipping. All right? And that I, for some reason that I don't entirely understand, spend an hour typing up. But anyway, you guys will read it and make me feel better about my life. Let's see here. So 2x plus 7. I mean, I feel pretty good about my life at the moment. Let's see here. For some reason, 3x minus 1. And there you go. So that, as you can see, it's reducible in z as well, right? honestly, folks, I'm not entirely sold on this theorem just yet. I don't see how it's... I personally would rather just try to reduce it in Z. Like, why bring fractions into the mix? Ugh. But anyway, this theorem is used in other theorems. Like, there's a point. All right, but yeah, sure.
What about the converse? Is it, if it's reducible over Z, then is it reducible over?
No. Well, I mean, the context is important here. We're starting with a polynomial in Z. I mean, there are definitely polynomials which are irreducible in Z, but are reducible in Q. Like we did, that was like my second example. Okay, so the next theorem here, in fact, the rest of this chapter, which I see I have not gotten nearly far enough into. This is what I get for not using the projector, I guess. Oh well. Where am I? Ah, yes. So here's our next theorem. It says that if P is prime, all right, and if f of x is an element of the polynomials over the integers, with the degree of f of x be greater than or equal to 1, then we'll define f of x bar to be the corresponding polynomial in ZPX, all right? Right. So for example, if I had f of x equal to 3x cubed plus 7x plus 2, then f of x bar in, let's say for z, z4x, all right, f of x bar would be 3x cubed plus 3x plus 2. Oh yeah, prime, I'm sorry. My bad. Let's make that a 5. Of course, you don't actually have to do the reduction. You can work with 7 and Z5 if you want. Whatever. All right, so what's the deal? What's the punchline here? Here's the punchline. It's so simple. If the reduced polynomial is irreducible over ZP, then f of x is irreducible over Z. This is an amazing theorem. All right. I will prove it next time for you guys. I think I still have like a minute so I can show you an example. For example, example 9. So if you look at like f of x equal to 30 x to the 7th plus 6x squared plus 3, all right? And I consider it modulo 2. What does it become? We have f of x equals to, what is it? I mean, 30 mod 2 is 0, 0. I mean, it's 3. So in other words, it's 1, right? And this is, oh stink, I have chosen poorly. Put an x on it, there we go, better. So 3x, which is x, and that's irreducible over Z2. Therefore, f of x is irreducible over Z. If we didn't have these theorem to work with, we would have to start thinking about possible ways of factoring the 7th order polynomial into like product of a quartic and a cubic or others. Oh, no. This is so much better. And then beyond this, there's this criteria by Eisenstein we'll go over next time, which is even more powerful still. Anyway, thanks guys. See what I